Hello class, welcome to section 4.7. Today we're going to go ahead and look at optimization problems. So what does it mean to optimize? Okay, so some things that you might think about when you think optimize. You might think best possible. Okay, let's see. Or you might think exact. Or even efficient, most efficient as possible. So in terms of calculus, what would it mean to optimize? And we did a little optimization yesterday in class and so to optimize something, you are thinking about getting the best out of it or maybe even the best cheapest option. So in those cases, it's usually a maximum or minimum. And in calculus, the way you find maximums and minimums is by taking your derivative and setting it equal to 0. Okay, so those are going to be your critical numbers. So that's where your max or mins could occur. So today we're going to be dealing with word problems, and then we're going to be finding the max or min values. So here's the steps for optimizing. So the first thing you want to do is find the formulas related to the problem. Usually there's two. There are some cases where there's only one problem. If there's two variables, you're going to want to have two equations. Then you're going to substitute the measurements you know into the equations. Combine formulas together through substitution, find the derivative, and then you're going to set your derivative equal to 0, and then solve for the max or the min. So here is our first problem. You want to build a rectangular enclosure for your dog with 60 feet of fencing. What is the dimensions of the fence that maximize the area? Okay, we want to maximize area. So whatever you want to maximize or minimize, this is what you're going to have to take the derivative of. Okay, so we're going to write an area equation and we need to maximize that. And then the other thing is we have talk about 60 feet of fencing. Okay, so we know we're going to have an area equation, but what does feet of fencing mean? Well, that would be the outside of your fenced in area, and so that would be your perimeter. Okay, so let's go ahead. I'm going to draw myself a rectangle. And I'm going to say this is X and this is Y. So the one thing I would say is area will equal X times Y. And then I also need to talk about my perimeter because that's going to be my 60 feet of fencing. Well, perimeter is all of it added up. So it's really X plus X, we'll have 2X plus 2Y. So those are my two equations. Okay, then you plug in any information you know, any other numbers. We know it's 60 feet of fencing. Well, that would be your perimeter. So I know that this is 60. Then what our goal is to make the area equation only in terms of all x's or in terms of all y's. It doesn't matter which one, so I'm just going to pick one and solve. So I'm going to get y by itself. Okay, so to get y by itself, I would subtract 2x. You could get x by itself. Either in this case, it doesn't matter. And then divide everybody by 2. So I have 30 minus x equals y. Okay. Now we go ahead and we take this piece and we plug it into our area equation. Because we're trying to make it all x's or all y's. So by doing this, we will have our area is equal to x times 30 minus x. So my area is now all in terms of x's. Okay. So now I'm going to distribute because it'll be easier to take the derivative of. So I'll have 30x minus x squared. And this is my area equation. I want to maximize area, so I want to take the derivative of my area equation. So now I'm going to go ahead and take the derivative. So my derivative is 30 minus 2x. And then we go ahead to find the maximum. We set our derivative equal to 0. And if I'm going to add 2x to the other side and divide by 2, so x is equal to 15. Okay. The problem says what are the dimensions? So we need to know the dimensions. So we need to know x and we need to know y. I'm going to plug it into here to figure out what y is. Y will equal 30 minus 15. So y equals 15. So the dimensions will be a 15 foot by 15 foot fence. So there would be the maximum area that I could gain with 60 feet of fencing. If it asked you specifically for the area, you would say that the area, take 15 times 15, 225 feet squared, if it asked for area. So that is example 1. So what your goal was to come up with 2 equations and think about which one you need to take the derivative of. Usually the other one you can plug specific number information into it. Then you would solve this for either x or y, plug it into your area equation, take the derivative of that and set it equal to 0. Okay. So let's go ahead and do another one. We have a liter, design a 1 liter or 1,000 centimeters cube oil can that has a cylinder in shape and uses the least amount of material possible. Okay, well, they're giving me this information, which is something cubed, and I would say I know that something cubed is volume. So I know that my volume of my cylinder is 1,000. So volume, how do I find volume of a cylinder? So I would provide you with this, but we could also logic through it or think through it. Volume is the area of the base, which in this case, if I drew it in, would be circles. It's a bad circle, but circles. The area of a circle is pi r squared times the height. Okay, so pi r squared h. The other equation is we are trying to use the least amount of material possible. Well, in order to make a can, that's really asking me about surface area, the outside. So surface area, once again, I would give it to you. Let's just quickly logic through what the surface area would be. The surface area would have 2 circles, right, the top and the bottom. And so the area of a circle is pi r squared, but I have 2 of them, so 2 pi r squared. Plus, now how do I figure out this, the circular part, or sorry, the like front or the lateral surface area of this can? It was a circle, top, and then we have this not paper, oh my gosh, can't talk today. The top is a circle. This middle part, if I were to cut it open and open it, it would actually be a rectangle. And we know that this is the height of h. This top piece here was really just the distance around here, which is circumference. Circumference is diameter times pi, but I'm going to keep it all in terms of radius, so I'm going to say it's 2 pi r, because 2 times r is your diameter. So then your surface area of this would be 2 pi r times h. Okay, so 2 pi r times h. And the good news is, if that doesn't make any sense to you, I will provide you those equations on your test. Okay. So then I have my 2 equations. Now I plug in what I know. I know that I have 1,000 centimeters cubed, so I'm plugging in 1,000 for my volume. And now I need to decide, do I want to solve this for r or h? Which one do I want to get by itself? So looking at this equation, I have an r squared here and an r and then an h here. There's only one h, so I'm thinking it'd be easier to get h by itself and then substitute it in here. So let's go ahead and do that. We will have, getting h by itself, divide by pi r squared. So h will equal 1,000 pi r squared. Taking all of this, plugging it in for h, and then we're going to simplify. So our surface area will equal 2 pi r squared plus 2 pi r, and then I have 1,000 pi r squared. So the first part stays the same. So we really have 2,000. My pi's will cancel. And then I have an r to the first over an r to the second. I'm going to rewrite it with a negative exponent just because it'll be easier to take the derivative. Okay, so I will have r over r squared, which is really r to the negative 1. Okay. Now I'm going to go ahead and take the derivative. So we will have that our surface area will equal 4 pi r. This is a constant, so it stays. Plus, actually it's going to be minus, because you bring down that negative 1. So bring down the negative 1. So negative 2,000 r to the negative second. Okay. So once again, we had our 2 equations. We made the one we're trying to minimize in this case, all in terms of one variable, and then we took the derivative. Now in order to find max and mins, we take our derivatives and set them equal to 0. And the easiest way to solve would probably to make all exponents to make all exponents positive. So I am going to go ahead and move the r squared to the bottom. Then what I'm going to do is add the 2000 r squared to the other side, and we're going to solve for a. Okay. So adding this to the other side, I have 2000 times both sides by r squared. We're just trying to get r by itself, so these will cancel. So 2000 equals 4 pi r cubed. We're going to divide by 4 pi. 2000 divided by 4 will give us 500 over pi equals r cubed. And then our last step is to get r by itself, so we cube root both sides. Okay. So r is equal to the cubed root of 500 over pi. If you wanted to type that in and get an approximate answer, let's see. You should get that r is equal to 5.419, and then this was in centimeters. And then we should also find our height. So we're going to plug it into the height equation. So it's going to be 1000 over pi times our r squared. So the cubed root 500. So I would make sure you can type this in and get the same answer that I am. So h will be approximately, make sure you put all of the bottom end in parentheses. And you should get that h is 10.839 centimeters. So there would be my radius and there would be my height for my can. All right. If you're having questions, feel free to write them down so you can come back and ask. But let's go ahead and move on to example 3. So we have a farmer. They have 2,400 feet of fencing and wants to fence off a rectangular field that borders a river. Okay, so we got a river. So basically there's straight across here. He needs no fencing along the river. So really I only need fencing here, here, and here. What are the dimensions of the field that has the largest area? Okay, so we want to maximize area. So we're going to take the derivative of the area equation. So let's think about it. What would the area of this be? I'm going to call this x and y. So area will equal x times y. But now I need to go ahead. I have to write my other equation. Well, he says 2,400 feet of fencing. Well, the fencing is really just talking about the perimeter, which is the outside. So my perimeter is a little different in this case. My perimeter is actually x plus 2y. And then I know it's 2,400 equals x plus 2y. So now I need to think about who would be easier to solve for. Would it be easier to get x by itself or y by itself? Okay, it's not going to matter plugging it in here. There's only one x and only one y. So I actually say it would be easier to get x by itself. So I'm going to subtract 2y to the other side. So x is equal to 2,400 minus 2y. Then I'm going to go ahead and take this and plug it in for x. And this one is actually very similar to example 1, except for you don't have this part of the fencing. And then I would distribute my y. So I have 2,400y minus 2y squared. Now that I have my area equation and I'm trying to maximize area, I'm going to take the derivative. I have 2,400 minus 4y. Then we set our derivative equal to 0 and solve. So 600, we divide by 4. So y is equal to 600 feet. Okay. Then we should go ahead and find x. Once again, the best way to find x is to plug it into here. So x will equal 2,400 minus 2 times 600. So 2,400 minus 1,200. So x will be 1,200 feet. So that would be my dimensions, a 600 by 1200 foot fence. Okay. So that is example 3. You're going to have one like this, I think, on your homework, but I'll remind you which one that is. Example 4, we're actually going to skip today, and then we're going to do our last example on our notes is example 5. Okay. So it says find the maximum possible area of a rectangle with a base on the x-axis and with 2 upper vertices that lie on the graph of the equation y equals 12 minus x squared. All right. So we are trying to maximize area of a rectangle. Trying to maximize area of a rectangle. So we know we're going to take a derivative of an area equation. And actually, they're giving us our other equation. So let's just visually think about this. If I go ahead and graph this, you could put in your calculator and graph it, but it has a height of 12. And it's a parabola. Since it's negative, it's opening downward. And it is symmetric across the y-axis, even though I didn't draw mine perfectly. And then what's going to happen is I'm going to go over a distance of x and go up. And over. And we're going to have this rectangle in here. So this is a distance of, in the positive x direction, and this is a distance of negative x in terms of your xy coordinate plane. Okay. So now we want to maximize the area of this. So let's come up with an equation for the area. This is really my entire base. Okay. It's really x plus x in terms of distance, so 2x. And then our height would be a distance of y. So our area this time is 2xy. And then my other equation is already here, and it's already solved for me. So I just have to take this and plug it in for y. So I have my area will equal 2x, and then my y, so 12 minus x squared. To make life easier, I would distribute before we take the derivative. Otherwise, you would have to go ahead and do a product rule. Okay. So there's my area equation. Now I go ahead, take the derivative to maximize. So I'll have 24 minus 6x squared. Then we're going to set it equal to 0. I'm going to add 6x squared to the other side, equals 24. Divide by 6. And then if I take the square root of 4, there's 2 answers, plus or minus 2. Okay, so that makes sense. Really, we're going a distance this way of 2 and a distance this way of negative 2. Okay, so find the maximum possible area of the rectangle. So we're actually finding the area this time. So I would say that our x value, we're going to say is positive 2. But the total base of my rectangle is really 2 times 2, which is 4. So this part right here is a distance of 4. And then our y, or our height value, will be 12 minus 2 squared. So 12, that's just plugging it into here. 12 minus 4, which gives me 8. So my height is 8. So my base would be 4, and my height would be 8. So my max area of this rectangle would be 4 times 8, which is 32, and then I would label it, I don't have it, so units squared. That would be my maximum area. Okay. So those are our notes for today. Here is your homework assignment, and we're actually going to go through a few of them, get you started together. Number 21 we're not going to do today, but we're going to do these 5 problems. So the first one is number 2. So maybe you want to pause the video, get out your homework, okay, your notebook, write this down, and I'm going to kind of go through each one of these. So 2, 3, 5, 6, and 11. Number 2. These ones are just a little bit more straightforward, but they kind of throw you off because they are so straightforward. It says find 2 numbers whose difference is 100. Okay, so 2 numbers. I don't know my 2 numbers, so I'm going to say the first number is x, and then I'm going to say the second number is y. All right, so difference. What does difference mean? It means subtraction. So I just need to take my 2 numbers, so x minus y, and says equal 100. Then it says whose product is a minimum. Okay, so the product is a minimum. So when I do product, it's multiplying, so it's really just x times y. This is who I am trying to minimize. So this is who I need to take the derivative of. Okay, take the derivative of that one. So here are my two equations. You're going to solve this one for x or y, plug it in here, distribute, take the derivative, and set it equal to 0. Okay? So go ahead if you want to pause it and do this one. This is as much as I'm going to talk about on number 2. But solve this for x or y, plug it in here, distribute, and then take the derivative, set it equal to 0. Okay? And that will get you your minimum and maximum for number 2. Number 3, it says find two positive numbers whose product is 100. So I'm going to do the same thing. Product is 100 and whose sum is a minimum. So I want a sum minimum, so I'm going to take the derivative of that one. So my first equation is product is a minimum, so our product equals 100. So product is multiplying, so x times y equals 100. And then whose sum is a minimum. So I'm going to use S for sum, is a minimum, so sum is addition, so x plus y. What you need to go ahead and do here is get x or y by itself, and I'm going to help you just on this one to remind you about negative exponents. Let's get y by itself. No reason in particular, just because. So y is equal to 100 over x. I'm going to now take this, plug it in for y. And I don't want to have to quotient rule this, so I'm just going to rewrite it. So it's going to be x plus 100, x to the negative first. Now you're going to take the derivative. Then you're going to set it equal to 0, solve, and get your values for x and y. Okay, so maybe you want to pause it, finish up number 3, but there is your help for number 3. Find the dimensions of a rectangle with a perimeter of 100 and whose area is as large as possible. Okay, this one is like our example number 1. Okay, this one's a rectangle. This is our perimeter, but the perimeter in this case is going to be, what was it? The perimeter is 100, okay? So this is like example number 1. Like, okay, so that one's similar to that. Number 6, find the dimensions of a rectangle with area of 1,000 meters squared whose perimeter is as small as possible. So what is different about this one? Well, they're giving us specific numbers for the area, but they are not giving us anything about the perimeter, and we want to minimize perimeter. So we are actually going to take the derivative of perimeter instead of area this time. That's why this one's a little different than example 1 and number 5. Okay, so area, I'm going to say we have a rectangle, x and y. So area is x times y. And then our perimeter is 2x plus 2y, right, if we add all of our sides together. Now I plug in what I know. I know the area is 1,000. Then I go ahead and get x or y by itself. I got y by itself, I think, before. So let's get x by itself, so divide by y. So these cancel. So x is equal to 1,000 over y. So now I'm going to take this, plug it in here. Now I just need to simplify. Once again, I know I'm going to take a derivative, so I'd have to quotient rule this piece, but I can rewrite it so I don't have to. So our perimeter will be 2,000. And then it's going to be y to the negative 1. I don't know why I was writing it so small. 2,000 y, when I bring it up, negative 1 plus 2y. Now what we're going to do is you're going to take the derivative. Then you're going to take that answer, set it equal to 0, and solve. Okay, so there's example 6. Number 11 is very, very similar. Oh wait, I lied a little bit. Never mind, this one's cutting it in half. It's not similar. So we'll walk through this one. But we have area of 1.5 million. Okay, so let's actually write that out. So our area is equal to 1.5 million square feet. Okay, use this number, otherwise you're going to get really tiny decimals and it kind of gets painful. But there's our rectangular field, and then it's divided in half with the fence parallel to one of the sides. How can you do this to minimize cost of the fence? Okay, so we have a rectangular fence, and then what he does is he divides it in two. Okay, so basically we need fencing for all of these things. So our perimeter, I'm going to call this x from here to here. So then this is also x because he divides it in half. Okay, so then if this is x and this is x, we got x here and x here. And then I'm going to call this y and y and y. Okay, so we want to minimize the cost of the fence. That would be our perimeter. Okay, right? You add the outside pieces up together. That's what you have to buy. So we need to minimize cost, which is perimeter. So I'm going to have to take the derivative of perimeter. So perimeter, in this case, would equal, I would say 4x plus 3y. And then the other thing I know is the area. So what is our area of the entire thing? We'd have 2x times y. So our area equals 2x times y. I know specifically what my area is. It's 1.5 million. And then we get x or y by itself. Doesn't matter. I'm going to get y by itself. So that's gone. So y equals, okay, 1.5 million divided will give me 750,000 if we divide it by 2 over x. Okay, so that's our x, sorry, that's our y value. So now we're going to take that and plug it in for y. Then we'll simplify. So our perimeter will equal 4x plus 3 times so we have 4x, and then we would really have 3 times 750,000. So 4x plus there we go, over x. And then in order to take the derivative of this, we take our x, bring it up. Okay, so we'd rewrite it with a negative exponent. Take your derivative, set it equal to 0, solve for x. Okay, so that is how you set up number 11, and then I think that's it. Okay, so hopefully you can get a good start on this assignment. If you have questions, we'll go over them in class tomorrow. Otherwise, I'll see you later and have a nice day.